The baseline temperature of the high Arctic winter is -40 degrees Fahrenheit. At this point, heat rapidly escapes through convection. There's no wood to burn for warmth, nor timber to construct a roof. By placing the structure 3 feet underground beneath a layer of sod and bone, the Thule Inuit shield themselves from the wind. Inside, the temperature stays at 70 degrees. The thermal load comes from just a single stone lamp. This is a specialized heat retention system that maintains a 110-degree temperature difference solely through geometry and material density. Today, we analyze the engineering of this underground machine. This thermal engine, using the power of simple geometry, turns a frozen wasteland into a stable microclimate. How can you build a permanent stronghold in a treeless desert where wind is relentless and night lasts 6 months? How do you construct it using only the bones of sea creatures and the earth itself? The high Arctic winter is a thermodynamic battle for balance in a system with half a year of complete darkness. There is no solar recharge, no incoming energy. The environment acts as an endless heat sink. In such conditions, a dwelling cannot just be a shelter, it must be a closed loop. Any heat loss is a mechanical failure. If the building lets warmth escape, the internal system fails. Wind is the main destructive force. We call it the heat thief. Across the flat, treeless tundra, there is no friction to slow the air. When a 40 miles per hour gale strikes a surface at -40, forced convection occurs. The wind doesn't just blow past. It instantly strips away the molecular layer of warmth from any exposed skin in traditional architecture. Wood forms the foundation it provides, roof beams and fuel for the hearth. Here, there is nothing, no timber to span a room, no wood to burn for heat. Without a fuel source, the Western concept of a home collapses. You can't rely on a continuous heat load from a furnace. You need a structure that works without external power. The Thule had to discover a different energy basis for life. They had to turn to the density of the earth and the skeletons of the sea. Building on the surface is a fundamental engineering hazard. A surface structure is a target. It is exposed to maximum lateral force and maximum energy dissipation. It's a thin-walled box fighting an infinite heat sink. For the Thule, the surface was a danger zone. To solve the surface problem, they changed the geometry of survival by moving the dwelling 3 feet into the ground. This shift from a temporary surface tent to a semi-subterranean pit house wasn't a matter of convenience. It was a calculated engineering decision to escape the atmospheric chaos of the high Arctic and enter a realm of geological stability. These pits, ranging from 10 to 30 feet in diameter, formed the base for a permanent winter strategy. They were designed as thermal bunkers, shifting the struggle for life from the volatile air to the predictable density of the soil in the high Arctic. The ground is permafrost. It is soil that has been frozen harder than concrete for millennia. For a modern builder, this is an excavation nightmare. For the Thule, it was a thermal battery. Although the air temperature above ground changes dramatically, sometimes plunging to -40 or -60 degrees Fahrenheit overnight, the Earth's temperature is stable. Beneath the active layer, the ground remains close to the freezing mark, 32 degrees Fahrenheit. This serves as a global buffer of steadiness. The ground offered more than a mere barrier. It functioned as a thermal mass that reduced the transfer of heat to the outside. During a -40 degrees Fahrenheit blizzard, having a chamber at 32 degrees Fahrenheit can mean the difference between survival and demise. The soil behaves like a protective heat source against severe cold. Contemporary building design combats cold by resisting heat flow. We employ slim insulation layers to impede heat transfer. Such materials boast high R values but have no mass. They are incapable of storing thermal energy. The Thule harnessed the planet's vast mass by excavating into the ground. In essence, they created walls as thick as the Earth itself. Thermal mass offers stability. Without any fire, a dwelling embedded in permafrost will eventually match the ground's temperature. This ensures the interior never drops to the deadly low temperatures of the outside air. Burying the dwelling into the ground also addressed the issue of wind. A building on the surface becomes a catcher of wind force, behaving much like a sail. By concealing the home underground, the Thule avoided the full impact of an Arctic storm, cutting the wind-exposed surface area by 85%. This turned the structure from an easy victim into a fortified shelter. The walls were no longer vulnerable to heat loss from wind, shielded by the Earth's enormous thermal mass. This reduced profile diffused the storm's mechanical energy. Normally, a 50 miles per hour wind striking a vertical wall generates a significant pressure difference. High pressure builds at the front while a vacuum forms at the back. This pressure gradient effectively pulls warm air from the house through even the tiniest gaps. By placing the walls underground and implementing a curved roof, the Thule made the wind glide over the building instead of colliding with it. Air flows over the dome with little resistance, entirely removing any pressure reduction. The dwelling merged with the terrain, unnoticed by the wind, thereby keeping the indoor environment stable and tightly sealed. Constructing into the ground was essential for heat management, but the Arctic Earth posed a physical obstacle. This permafrost, soil frozen for millennia, has compressive strength similar to that of concrete. Advancing each inch downward demanded hours of handwork using picks crafted from walrus, ivory, or caribou antler. The Thule tackled the permafrost challenge by engineering over time. Rather than combating the frozen ground with sheer power, they relied on the sun as their main digging instrument in the short Arctic summer. The uppermost inches of permafrost thawed into a muddy layer. The Thule removed this mud with bone hoes and stone shovels, revealing the next frozen layer to sunlight. This was an ongoing, multi-year task of clearing and upkeep to compensate for the complete absence of wood. The Thule looked to the ocean. One bowhead whale yields about 60 tons of organic construction resources. The main roof supports of the dwelling came from whale jaw bones, known as mandibles. These bones have a natural curve and can grow up to 15 feet long. In structural design, an arch outperforms a flat beam by turning tensile stress into compressive force. The Thule leaned these huge jawbones together in a cone or dome shape, forming a framework of remarkable strength. Those jawbones supplied the required height and width for a home housing several families. This formed an arched ceiling able to bear many thousands of pounds of outside force. The whale's ribs made up the secondary framework, which was bound horizontally across the jawbones to form a sturdy crisscross lattice. This lattice acted like the lath in contemporary walls, offering a dependable foundation for the roof material. For the more intricate parts of the structure, the scapulae-wide, flat shoulder blades were employed as natural shingles. These were positioned over the openings in the rib lattice to provide a partially waterproof covering, or served as movable dividers. To arrange the interior layout, each skeletal element was chosen based on its shape and capacity to evenly spread the roof's weight. Instead of nails or wooden dowels, the Thule fastened the connections of this bone stronghold using baleen. The whale's keratin filtering plates represented a crucial engineering decision. In contrast to leather cordage, which tends to stretch when wet and break when dry and brittle, baleen is a stable polymer material. While it remains pliable during assembly, it hardens and actually contracts when frozen. This results in a tension-based connection that outperforms metal in freezing temperatures. The lashings of baleen functioned like a structural glue, tying the whalebone beams together into one cohesive framework. This could bend under snow loads without breaking. Insulation formed the outermost layer of the building. Initially, the bone skeleton was wrapped with thick seal or walrus skins to establish a barrier against the wind. On top of that, the Thule added a 3-foot-thick coating of tundra turf. Tundra turf isn't merely soil, it's a compact fibrous mass composed of moss, peat, and living root systems. This substance offers an extremely high thermal resistance, yet its real advantage comes from its living characteristics. When the sod was placed with roots pointing inward, the vegetation stayed alive inside the house's heat-insulating envelope. Gradually, the root networks kept growing a little, their strands weaving together to form a wind-resistant covering that could mend itself. The dwelling was no longer merely an immobile construction. It had become a biological geodesic dome. It functioned as a living apparatus, harnessing the Earth's density and the ocean's physics to forge a refuge. The sod supplied thermal mass, the bones offered tension, and the roots ensured an airtight seal. However, the seal's very effectiveness generated a deadly contradiction. It constructed an almost flawless heat-trapping system. In their effort to overcome the cold, the Thule had fabricated a completely sealed space. They had introduced a fresh adversary, the accumulation of carbon monoxide and carbon dioxide originating from their oil lamps and respiration. To endure their own construction, they needed to shift from solid-state physics to fluid dynamics. They needed to gain control over air circulation. In the present day, these remains function as a model for sustainability. The Thule sustained a temperature difference of 110 degrees Fahrenheit without any fossil fuels or external energy input. They demonstrated that the pinnacle of technology is not the one that uses the most energy. Rather, it is the technology that operates in optimal alignment with the principles of the environment. They did not merely endure the Arctic, they devised a method to become part of it.